Okay, so we're recording. So last time, right, I'm remembering, before we get into the math, I just want to give you all a quick reminder. Don't forget, here we are, Wednesday, September 21, and look how close we are to the first exam. Just a quick reminder, just a heads up. So Monday is that first exam. Notice, again, I think y'all all know this already, but the color coding is going to indicate what the fair game material is. So notice, yet to be determined is what are we going to finish today. I'm optimistic about 2.5. But anyway, whatever gets filled in here will complete the fair game material for the course. And of course, the fair game material includes whatever's in the book in these sections, but also whatever we cover in class corresponding to those sections. And then, of course, modulo what the course content syllabus says. That's certain materials excluded. Not responsible for that. Okay. All right. So that noted. Let's move it along. So last time we were talking about intermediate variables as a point of view on the chain rule. Right now, let me remind you real quick first. The primary point of view I want you to have on the chain rule is that the chain rule says matrices multiply. Derivative matrices multiply. Because, in some sense, what this matrix does is it connects that vector to that vector, and what this matrix does is it turns this vector into that vector. So, if you want to know, what do I do to x prime to get z prime? Well, apparently, I need to first multiply by this green matrix and then subsequently multiply by this blue matrix. AKA, I need to multiply by the product of those two matrices. So, once you see the sort of the vector's point of view, I think it's actually a pretty plausible statement that that purple is blue times green. Again, that's the primary point of view that I want you to take, but in certain special cases, it is actually pretty nice. Where am I? Here it is. Pretty nice to be able to think about a variable's point of view. Most of the time, vectors are the more natural way to think about what's happening in this class. But sometimes variables are useful. So picking out one of the elements of the product derivative matrix, right? And you notice pretty quickly that element is a dot product of that row with that column, which therefore gives you this expression for that single variable, for that single coordinate partial derivative. Okay. So, good thing to know. Much more to say about this. A quick reminder, though, don't make the mistake of thinking that you can cancel the y's. That, of course, is nonsense. You cannot do this at all. For one thing, it obviously gives you the wrong answer. If you cancel all these terms, then you would get partial of zi with respect to xj a bunch of times, as opposed to the one time that, of course, you should. So aside from the fact that it gives you wrong answers, it's also just logically a non sequitur. So remember, when you write this down, right, this is not a ratio of two independently well-defined, uniformly, consistently defined things. It's just not what this is. This is notation representing part of what's going on in a certain scenario. In this scenario here, most of the y variables are required to be constant. Y1 is the only y variable that's changing. Well, there's a very different story going on over here in this blue side of this term. One of the x variables is changing. If one of the x variables is changing, all the y variables are going to be changing, right? So they aren't going to be constant, or they certainly are not required to be constant. Almost certainly are not constant. Because the x's are changing, the inputs to the y's are changing, and therefore the y's are changing. So these are two different stories. And in both cases, y1 is changing. But these are, again, separate scenarios. And in the same way that you can't, look at the answer from one question X equals 5 was the answer to one question, and then use that in, exercise 27 later in the homework. Well, of course not. They're different scenarios. Of course they're going to be different. Likewise, these are different as well, and you cannot cancel those. Okay, so this is what we talked about before. Is everybody good? Okay, so how do we think about this equation, and why do we call it intermediate variables? This is the way I like to think about it. I think this is very satisfying. Let's look at this sort of one term at a time. What's going on with this term here? And what I claim is that term corresponds to how changes in xj propagate along this path. And if you change x, again, we're holding all the x1 through, all the x's except for xj are being held constant. If you wiggle xj, then changes are going to propagate along this path and contribute to changes in zi. Now, how much change would there be? Well, however much change there is in xj, I can relate how much change there is in y1, because the change in y1 per unit change in xj, ignoring all the other input variables, that's the definition of the partial derivative. So this first step along the way, I should say, that first step along the way is that factor right there. Whatever change you make in xj gets scaled up by, along this part of this path by whatever that partial derivative is. And then, how does, the amount of change that you see in y1, how much does that scale up to contribute to how much zi changes? Well, it's the partial of zi with respect to y1. And keep in mind, when I say how much does this change cause that to change, I want to talk about just this change only. Yet there are other paths. We'll get to those other paths. Right now we're focusing on just this one path, and I want to know just how much the change in y1 contributes to changes in zi. And the way we isolate that is we ignore the rest of the scenario, pretend all these other y's are constant, and look at zi as a function of just y1. In other words, partial derivative. So each term, you'll notice then, corresponds to a path. And so I'm going to say here, likewise, ... other paths. And then now let me go to the last one just to have something to circle. The changes that propagate through ym correspond to that term. And again, you can look at the independent parts. You can look at this part, and those are the two factors that are in this term. So that's the way I think about it. This is what I encourage you all to think as well in terms of, how do you remember this formula? And that is that there's terms corresponding. Let me clean this up. There's terms corresponding to each path. So there's a path through which changes propagate from xj to zi. That path has a term. There is you might say, a next path. Right? There would be a next term in here that I didn't have room to write down. And then et cetera, et cetera. And then finally, this path corresponds to that term. Okay. And then side note, notice each one of these paths corresponds to one of the y variables, right? The purple path goes through y1. The red path through y2, specifically. So not only do you get a term corresponding to each path, but you might say you get a term corresponding to each intermediate variable. These are what we call intermediate variables, and thus the name of this point of view. So think about terms corresponding to each intermediate variable. And again, just to be clear, the intermediate variable y1, you can see that this is the y1 term because you can see that intermediate variable in the term. And then et cetera, and let's see the last one we used, dark blue here, so the ym term right there. So for each intermediate variable, you get a term. Okay, so it's nice in the sense that you can just kind of write equations down and you don't have to write down, matrices for all their power. They are kind of big and clunky, right? And if you need, I just need this one partial derivative. I don't need the whole thing. I just want the one partial derivative. You can just write down that one equation, write down just exactly what you need and go straight to it. So let me show you an example of that. Here, we've got a couple of functions. The y variables are functions of the x variables. The z variables are functions of the y variables. And the question here is to compute the partial of z2 with respect to x2. Okay, so there's z2 and partial with respect to x2. I want to compute that partial. Okay. So what we're going to do here is first, I like to make what I like to call the roadmap. We want to see a diagram representing, which variables are functions of which other variables. And I like to think of the variables as going kind of left to right. When you compose functions, you might think of them as composing left to right. And so here I've got the y variables as functions of the x variables. And here I've got the z variables as functions of the y variables. Right, so I've kind of diagrammatically represented the given algebra. Quick pause. How are we doing? Is everybody okay? Yeah. Okay. All right, so again, we're interested in the partial of z2 with respect to x2. Well, there's z2 and there's x2. And if that's what I want to compute, partial of z2 with respect to x2, let's start thinking about paths and intermediate variables. What are the different paths by which I can get from here to there? And, there's two of them. There's what you might call the y1 path. And hey, check it out. Here's my y1 term. You can see the y1 is the intermediate variable, and you can see that we're looking at z2 outputs and x2 inputs. So that's the y1 term. And then, there's also this path through which changes can propagate. You might call that the y2 path. And here's the y2 term. You can see y2, the intermediate variable, and you can see again still z2 is the output and x2 is the initial input. So two paths, two terms. No matrices. Didn't have to write down any matrices. One single equation that gets exactly to the one partial derivative that I've been asked to compute. That's all I was asked for, so it's convenient to go straight to it. How are we doing? Yes.
So why are you adding the two paths together?
Yeah, because when changes to this variable happen, there's actually several consequences to xj changing, right? On the one hand, xj changing causes y1 to change. And independent of all the other y's, whenever y1 changes, that's going to cause zi to change somewhat, right? But in parallel with that, at the same time, there's a whole separate thing happening, which is that y2 is changing as well, right? And changes in y2, independent of all the other y's, including independent of y1. When you change y2, that's going to cause zi to change also. So these are parallel propagating paths, and so their contributions add. Does that make sense?
Yeah.
It's a good question. Yeah. Yes.
So you have more intermediate variables, like more powers?
Yeah, it gets weird. What I would do there is apply the chain rule sort of, in natural bite-sized chunks. And then once you've computed whichever partials you need from this part, then move on and combine, these partials with the next step partials and use the chain rule there. So just I wouldn't try to go more than one step with this point of view at a time. Now this is a vote for, by the way, the matrix point of view, because if you have a composition of three functions, well, then you just have a product of three matrices in exactly the order you would think, and it's exactly what you would hope. So with matrices, it's no problem at all. matrix multiplication does all the bookkeeping for us. With intermediate variables, it's weird. Yeah, another good question. Thank you. Okay. A couple of details left to be resolved here. We've got to actually do the plug and chug, and I'm mostly going to leave that to y'all. It's just partial derivatives, right? But partial of z2 with respect to y1, what's that? Well, here's z2. Whoops, I missed. Here is, let's try that again. There we go. There's z2. Explicit formula given, right? So what is the partial of z2 with respect to y1? Well, you got to take the partial of this with respect to y1. You get 3y1 squared. So just look at which variables are which formulas. Take the partials accordingly. Off you go. Okay. Is everybody happy? Okay. All right. Do be careful about what I call confusion of variables. I'm going to show you a silly single variable example first. It's laughably wrong, obviously wrong. Again, the purpose is, to the extent that you understand the single variable example, you'll be, persuaded already in advance of the multivariable example that we'll get to in just a second. But here's a perfectly good function. Here is another perfectly good function. Nothing wrong with it. Right up until the point where I decide that I want to compose them and start doing stuff. And I claim that that when I compose, a problem is created that's about to reveal itself. So let's naively ask, what is the derivative of the composition? And let's hastily, sloppily say that the derivative of the composition is the product of the derivatives. And hey, these derivatives are easy to compute, aren't they? The derivative of x cubed is 3x squared, and the derivative of, x squared is 2x, and you multiply those together per that formula, don't you get 6x cubed? And of course, that's wrong. I don't think there's any mystery there. That's wrong. I mean, in fact, if you look at the composition itself, the composition is x cubed, x to the sixth. And the derivative of x to the sixth, we know it should be 6x to the fifth. So clearly wrong. So the obvious fix is to recognize that when we write G prime, very importantly, G prime has to be evaluated not at x, but at f of x. That's the Newton notation for the chain rule. And so technically, I need to. I shouldn't have x there. I should have f of x in there as the thing that I square and multiply by 3. And that makes the algebra work out correctly. Okay. Now, you can do that, but here's the even better, in my opinion, way to do this, and that's to recognize that there is something intrinsically unnatural by how this is written once I get to this composition. And that is, look, if I'm composing f and g, I've got to be clear and unambiguous and unconfused about what are the names of the variables that are going to play these various roles as I compose f and g, right? So I want to stick f and g together like that. So what names am I going to use for the variables? Well, you can just fine say that I'm going to call this input x because I already have f written as a function of x, and that's convenient. No reason to change that. But what should I call the input to g? Oh, whoops, I'm sorry, wrong color. What should I call the input to g here? Tempting to say, well, it says right here g is a function of x. But no, it's not. I mean, it's just not, right? X is the input to f. The input to g is the output from f. I can't use x as the name for the output from f. It's already the input to f. So that's literally a confusion of variables. We're using the variable x here to represent two different things. It's both the input and the output from f. And that's just not good. Everybody see the problem? So this is so easily fixed. So easily fixed. all you got to do is just recognize that, a bad choice to call this x. Right? Of course it's a bad choice. We already got a job for x. X is over here. So just call it something different. We'll call it y. We'll reinterpret the function g as being a function of y. It doesn't change the function. It's still the same function. Right? If I write g of y equals y cubed, that's exactly the same function as g of x equals x cubed. They both say, hey, whatever you give me, I'm going to cube it. Same exact function, just rewriting it in terms of a different dummy variable. And in so doing, now I have an unconfused notation for the functions. And I can be as sloppy as I want in how I write down the chain rule. Derivative of compositions, product of the partials, fine. No problem. What is g prime? 3y squared. What is f prime? 2x. All together then, I get 6y squared x. And wait a second. What is y? What's this y thing here? I got to figure out what to do with that y before I wrap this all up. Well, y says right there. Y is f of x. AKA x squared, and of course you just stick in that x squared, then it all works out. And you get what you're supposed to. So just don't confuse your variables and everything's glass smooth. No problem. Okay, so again, that's all single variable. I know you know single variable, but I wanted to make the persuasive case about confusion of variables so that when we do the same thing in multivariable, it doesn't seem unnatural. And you find yourself very often in the same exact situation where you're given a perfectly good function, not a thing wrong with it. You're given another perfectly good function, not a thing wrong with it, right? There's no reason to be suspicious when I write this down that something bad has already happened. Because there's a couple of functions, we haven't been asked to compose them yet. There's no reason to not like this. Again, until you are asked to compose them. Once you're asked to compose them, then you got to recognize that whatever you use as the input to the first function, dibs has been called. You can't use those variables for other things. You certainly can't use them for the outputs for that same function, and therefore you can't use them for the inputs to the next function. You're going to have to rewrite that next function in terms of other variables, say u and v, perhaps. No particular reason. And then it's all downhill from there. Let me pause before we get into the resulting algebra. Everybody see how this is same scenario that we were in the single variable case, just, multivariable. Same problem, same remediation. Okay. All right. Yeah, so take derivatives, right? Here's the derivative, here's the derivative matrix of that. Here's the derivative matrix of that. Just straight up multiply them together. Naively, don't even worry about it. The notation's doing the bookkeeping for us. I don't have to worry about, is this the real x, or is this the x that's actually the output, and it's actually it's the first input out, the first output coordinate from the function. No, it's v. It's perfectly clear what v is. Okay. And then, you can multiply them out. Now, if you want your answer, if you think about it, your function here, this composition, is a function of x and y. And a pretty persuasive case could be made that the natural way to write your answer about the derivative of a function of x and y is that your answer should be in terms of x and y. And so when you get around to multiplying, putting a box around your final answer, maybe we really should rewrite what u is in terms of x and y. And don't forget what it is. U, being as it is the first input variable to g, it is also the first output variable from f. So u is x squared plus y squared. And just, go ahead and toss that in to your expression. Everybody see what happened there? Just keeping track, using the diagram to remind you what things are, and then interpreting appropriately. And then likewise for V, of course, V being the second input to G, it's also the second output from F, and therefore it's x squared minus y squared. So this V we rewrite as x squared minus y squared. Okay. Yes? Yeah, I made them up. Yeah, that's right. I had sort of the freedom to, here, everything's in terms of X and Y, and I just needed another name. And notice it's a dummy variable, so it doesn't actually matter. Whatever I called it, it got eliminated in the end. My answer is all in terms of X's and Y's, right? So it's just a placeholder, and yeah, you can call them whatever you want. You can do a P and Q or whatever. Yes?
For G, why is U on the top, G on the bottom, but then you put V on the top and U on the bottom in the next parentheses?
I'm not following. Say where is this?
Like right under where it goes to G, then when you switch out the variable from X to Y to U to V.
Yeah? Want to do this?
Yeah. Why is V on the top and QV squared and U on the bottom?
Well, so keep in mind, X is I'm rewriting as U, right? And Y I'm rewriting as V. So this Y is also V.
Okay.
Does that see what I'm saying? Yeah. Yeah, so you just got to be consistent. Yeah. That's right. You're good?
Yeah.
Yeah.
Thank you.
Okay. Yeah. Okay. Good deal. Okay, so let's talk about how to do second derivatives. It gets a little bit weird in a way, but ultimately all of the weirdness of taking the second derivatives with the chain rule are resolved by being careful with your diagrams, by interpreting carefully and correctly which variables are functions of what, then just don't go too fast. And use the chain rule as needed. It's all about making sure you interpret everything correctly. So let's just dive in with an example. This is a classical first example. So starting off with Z is a function of X and Y. So again, put that on your diagram. And then R and theta are the usual polar coordinates. And of course, what that means is that X and Y are functions of R and theta in the usual way. Okay, so we have a composition. Z is a function of X and Y. X and Y are functions of R and theta. Okay. And we have been asked to compute second partial with respect to R. So again, notice that is a chain rule problem because there's Z and there's R, and intermediate variables and all that. Okay, so first, I'm going to write down the first partial. Chain rule with two paths, therefore two terms. There you go. Really quick rewrite, an alternative notation for the partial of Z with respect to X. Likewise for the partial of Z with respect to Y. It's going to end up being kind of convenient here momentarily. Question.
Doesn't theta affect X and Y as well?
Absolutely. But just we're interested in taking partials with respect to R, and when you're taking partial derivatives, that means that for the purposes of this whole calculation, we're treating all the other input variables as constants. So theta, for the further purposes of what we're doing here, is a constant. Yeah, good question. Absolutely. Yeah. Okay. All right. And then of course now this partial derivative right here, partial of X with respect to R, we have an explicit formula for X in terms of R and theta, and you can just straight up compute its partial, no problem. Right? You take the R partial of R cosine theta, and that's cosine theta. And then likewise here. Okay. So that's first derivative. No problem. By the way, I'm going to momentarily ignore this diagram. This is the, I'm going to make that a reveal, so try not to look at that just yet. And momentarily ignoring that we have that, let's ask, how would I take a second partial? Well, I would take the first partial that I've just computed, and I would take the R partial of that. Right? The R partial of the R partial. Yeah? Okay. A couple things we can write down. I mean, we've already got that theta is a constant. Let's remind ourselves over here. R is our variable. So theta is a constant. If theta is a constant, that means that cosine theta is a constant, sine theta is a constant, which, pretty convenient. Lucky break. You won't always get that lucky, but these constants, of course, then factor out, and you can separate out, two terms, and we get really this expression that we need to move on from. Okay, so everybody good so far? Here's where it gets delicate. Here's where a lot of students crash and burn. And that is making sense out of what this is saying right here. Partial with respect to R of Zx. A lot of students will write, and I'm going to put a question mark over this. A lot of students will write Z XR. I claim that doesn't make any sense. I claim this is garbage. ZXR is not a thing. So let me elaborate on why that is. I mean, how come I can write ZX? Let's see here. I can write ZX to indicate a partial. Why can't I do it for the other partials? Well, here's the thing. Z is a function of two variables. It's a function of two variables, x and y. Right? I could instead view it as a composition. I could view Z as being a function of, by way of the composition, function of R and theta. Again, happens to be in this case, again, a function of two variables. Fine. No problem. Importantly, R and theta are independent. You can do whatever they want. Likewise, X and Y, independent variables. Right? So Z is got to be thought of, whatever variable you're taking a partial of, you have to understand that variable as being the value of a function of independent variables. And if you write ZXR, the seeming suggestion is that Z is a function of kind of all of this all at once. And they're just not independent variables. Right? I mean, here, just as an exercise in silliness, suppose I were to insist, I'm going to think of Z as being a function of these four independent variables. What would be the R partial of this Z here? What would that look like? Well, the R partial would mean that I'm going to view R as being, I hit the wrong color. I'm going to view R as being the variable, and then I'm going to hold all the other variables constant. Well, that's nonsense. It's not. You can't, because if R is changing, X and Y are changing. You can't hold them constant and change R. It doesn't make any sense. The whole thing, it just doesn't make any sense at all. So you can't think of Z as a function of those variables, and therefore this notation. It just doesn't mean anything. It's not that this is unpreferred notation. It's that it's meaningless. Does everybody see the gripe? Okay, so that's the what not to do. All right, so what do we do? And what I like to do is come to this diagram that I had crossed out, and notice I've added some things. I've added here ZX that wasn't in the original diagram. Right? I've added ZX in particular as being a function of X and Y. Now, is that reasonable? Is it the case that ZX is actually a function of X and Y? Well, yeah, of course it is. Because Z was a function of X and Y. So therefore, its partials also functions of X and Y, as previously noted a couple days ago. So zx is a function of x and y. Let's represent it as such on the diagram. Then likewise, zy, also a function of x and y. So this is an honest picture of what we got. In some sense, we have kind of two new variables. And by the way, this is why I like to use the subscript notation here. It just makes them look more like variables that I can talk about partials of with respect to other variables. So sure, you could read it. You could leave it as a sort of fractional notation, but I think it looks better like this. And so interpreted, what is the partial of zx with respect to r? Well, there's zx, there's r. Look at paths, look at intermediate variables, and write down terms accordingly. Right? So here's the first path from r to zx. It's what you might call the x path. Right? And so here's the corresponding x term. And then here's the second path, you might say, from r to zx. That is through the intermediate variable y. That gives us this term where the intermediate variable is y. So altogether, it's just a chain rule application. I compute the partial of zx with respect to r, interpreting that there's two intermediate variables and therefore two corresponding terms, and this is just a chain rule. What do you think? Everybody okay with that? Yes.
Let's say you had like zx is like x squared. You just plug in like r squared for x. What
I want to do here, I want to talk about how ideas connect to each other here, right? So there are some scenarios where you might have additional information where you don't even have to use the chain rule at all, right? And so I recognize that, but it's taking us in the wrong direction because I want to explain the ideas, right? And so this the best way to show how the concepts and the objects relate to each other is to assume that you don't actually know much about them. Right, and so there's that. There's another point I'll make, and so thank you for the question. It's another point that I think is important. Let's see here. Yeah, right. So let's look at this question here that we've already gone through, where a couple of functions were given. We're asked to compute the derivative of the composition. Keep in mind, I know I've said it a million times before, I'll say it a million times again, this is not a class about answers, it's a class about ideas. Right? So when you see a question like this on the exam, part of your job as a student taking the exam is to ask yourself, okay, I've been asked to compute a certain thing. Why would he ask me to do this? What's he getting at? What's he want? What does he really want? This is an attempt to test the student understanding of what idea, right? Because it's the idea that I'm interested in, right? So notice, I suppose technically I could take these formulas and plug them into there and explicitly compute this composition, G compose F, as a great big function of x and y. Right? And then I could just compute the derivative matrix, just, as a series of partials. No chain rule required. So that would get me to the answer. Right? But again, that's not what we're interested in this class about ideas. Back to the previous question, what is the purpose of this question? Why would this be on the exam? That is pretty clearly, this is the purpose of this question, is for the student to demonstrate proficiency with the chain rule, right? And so when you see something like this, you should interpret that the Math 219 relevant solution is the one that uses the chain rule and multiplying matrices like this. It gets you to the same answer, but it shows the relevant ideas. Does that make sense to everybody? Okay. So just keep in mind the ideas are what I'm interested in, and you have to interpret accordingly. And sometimes I won't say specifically use the chain rule because I want that to be your job. I want you to have to interpret, right? I want you to have to diagnose the question appropriately. So it's left to you to interpret instead of. Sometimes I'll explicitly say, but sometimes. So that was a bit of a digression, but I think it's an important point. Is everybody happy with that? Does that make sense? Right? Okay. Okay, good. Thank you for the good question. Okay. Okay. So we took the partial derivative here. Yeah. And then, we've got to do the same thing for this right here, partial of zy with respect to r. There are those. And again, there is an x path. There's the x term. There is a y path. There's the y term. And so altogether, this partial, by the chain rule, is the sum of those two terms. Again, it's just the chain rule using the diagram appropriately amended. What do you think? Is everybody happy? Okay. Yeah. And then it's all kind of downhill from here. You've got a couple of partials that you can compute, right? I can compute that. I can compute this, because I know those functions explicitly, so we can go ahead and plug that in. And then I can think about notation zx partial with respect to x. Yeah, I can rewrite that as zxx because again, z is a function of just x and y, and taking the x partial and then another x partial, perfectly fine, no problem. That's exactly what that means. And then likewise, that. Don't forget, of course, there are these constants that we had already established. Here, they come along for the ride. They don't just disappear. And then, multiply, collect terms, and you end up with an answer down here. Everybody happy with this method? So I want to emphasize the big tricks here are make sure you understand what's a function of what. That's the purpose of this supplementary diagram down here is to visibly recognize, diagrammatically represent that this is a function of those. Right? It's not that this is a function of those. That doesn't make any sense. Okay. Make sure you have a fully documented diagram representing what's a function of what. Move slowly and carefully. Always make sure to remember what is being held constant as you're taking which partials. Right? Chain rule. Okay. All right. So let me show you an application of this. Y'all have already seen this thing called the Laplacian operator in at least one homework exercise. It is really important in physics. Lots of ways. It's a critical part of what we call the wave equation and what we call the heat equation, and various other physics things that are all very important. So it's this hugely important operator. And this is the formula for it. This is, by the way, also the easiest way to motivate the Laplacian operators in rectangular coordinates, just as it's written here. So this is an important point of view. The problem is that very often the function f that we want to apply it to, very often we want to do that in spherical coordinates. So it'd be nice to know how to rewrite the Laplacian in spherical coordinates. And here's the outrageous looking answer. And if you think that's long and ugly, try deriving it. There's a whole lot of algebra that goes into deriving this. Now, the way you would do so, and I'm not saying you should, but if you up for a challenge and want to, see if you can ring the bell on second derivatives with change of variables. Excuse me, with the chain rule. You can, for example, compute second partial with respect to theta pretty analogously to how here we computed second partial with respect to r. I mean, this is a function of two variables, but we're computing a second partial by viewing the given rectangular coordinates as functions of our new non-rectangular coordinates and applying the chain rule, right? So you can just exactly the same way, you can compute that. And likewise, that. And then that. All with the same chain rule, all analogous to what we did on the previous page. Just a lot of algebra. Again, very clunky. But if you compute all this stuff, compute this thing, and that thing, and that thing, all using what we saw on the previous page, again, analogous to the previous page, what you will find is that you get that. You get the Laplacian. So this big mess down here is known as the spherical Laplacian. And again, it's just applying the chain rule to that diagram. Okay, so what is this good for? Why would anyone want to... given the choice, right? Which one do you like better? I think most people would look and say that one looks a lot nicer, doesn't it? Okay. Well, hold your judgment. Here's one of the important physics equations that the Laplacian relates to. Is if you have a gravitational potential or an electric potential. Those away from the masses and charges have to satisfy this equation. The Laplacian is equal to 0. So let's entertain the possibility that, by the way, ends up being true, that this function right here might be a solution to that equation. In other words, that you might be able to stick this in there and that this blue equation might work. So how would we test, how would we confirm that in fact this is the right solution or a valid solution? So okay, well here's how you do it. You have two choices. On the one hand, you can use that rectangular Laplacian that we all thought we liked, right? Along with the rectangular formula for that candidate function. And we can punch this up. And so feel free. If you want, but you got to take a second partial with respect to x. The first partial is already going to be annoying. You got the quotient rule. There's going to be fractions, fractional exponents, numerator, denominator. Oh gosh, it's going to be a lot of work to actually punch that up. Okay, so I'm going to call that an undesirable solution. But now let's look at the ugly one that everybody didn't like. Here's our spherical Laplacian. Here now is our spherical formula for our candidate function. Right? And let's start taking partials. Okay, first thing I need to do is I need to take a theta partial of that expression. Oh, there's no thetas in it. 0. This whole thing just disappeared. Right, that's pretty sweet. Gone. It's 0. That whole term I can ignore. Because I'm applying a spherical operator to a function that's very easily written in spherical, and I'm using the right tool for the right job here in some sense. So the things fit together nicely. Next, let's take the phi partial of that. Oh, again, no phis. Therefore, that's 0. Therefore, this whole term, boom, goes away. Just massive chunks of this ugliness are just dropping out. And then lastly, okay, we do have to actually do a little bit of work here. And that is, I'm going to have to take a rho partial of this, which you get negative k over rho squared, which you then multiply by rho squared, which gives you negative k. And what then is the rho partial of negative k? Well, that's a rho partial of a constant. 0! So again, I get 0, and we win. This thing does indeed add up to 0. It's much easier to do in spherical coordinates and rectangular coordinates. The familiar, yeah, sure, it's familiar, but a lot uglier to work with. And again, this is a very natural scenario. We're thinking about gravitational electric potentials, as very commonly we want to do. This, by the way, that we've just confirmed, this confirmed solution is the potential function for a single point mass or a single point charge. That's what it actually looks like. So this is a very, I would call this a basic and fundamental computation to understanding a fundamental feature of how the world works. Namely, if I have a mass and it creates a potential, what does that look like? Take your pick. Which one of these do you like better? I like this one. Okay. Let's see. And we're out of time. We'll call it a day there. Okay. Y'all have a good Wednesday. See you on Friday. And good luck studying for the exam. Oh, and of course, as usual, don't forget to let me know if I didn't